The development of the thermoacoustic Stirling engine has made great progress recently. It is now planned to produce all components using a 3D printer. The upcoming pressure charging will enable much higher performance levels to be achieved. The aim is to enable everyone to build their own open-source electricity generator. In my last videos, I showed the conversion of the power extraction unit to use a membrane instead of a piston. This can be produced entirely using a standard 3D printer and allows the resonant frequency to be adjusted by varying the tension of the membrane. The test runs were very successful and, surprisingly, the engine is now able to start on its own as soon as the acoustic wave inside is strong enough. This greatly simplifies the power boosting pressure charging process, as no additional starting mechanism is required.
And now it starts by itself.
To simplify the construction of the engine and eliminate leaks, I redesigned all parts and optimized them for 3D printing. Only the high temperature components are still made from conventionally manufactured metal parts. However, this one is also going to be redesigned soon and printed relatively cheaply by a 3D printing service using metal or ceramic. Trials are also underway using homemade heaters made from 3D printed ceramic or cast concrete. The compliance is an important part of the feedback loop and, when correctly designed, can greatly increase engine performance in conjunction with the inertance. In short, to achieve optimal resonance, it should be as short as possible with a large volume. I printed it solid with 100% infill and 5% over-extrusion using PC/PBT CF. The material is rock hard and, in terms of strength, almost comparable to aluminium. It was very difficult to remove the supporting structures. I had major problems with warping when using PA12 CF. The part is simply too large and solid for my basic printer, which doesn't have a heated build space. The individual components are now connected using clamping flanges. These are completely tight, quick to assemble and well suited for 3D printing. Thanks to Rob from Discord for his suggestion. A quick pressure test showed that the compliance provided a good tightness even without sealing.
Quite tight.
The T-junction splits the acoustic wave into the feedback loop and the power extraction unit, where the energy is converted. There are also connections here for pressurization and pressure measurement. I printed the T-junction with a solid 100% infill, but this time using inexpensive PETG. When designing in FreeCAD, I forgot to include a few fillets in important places, and it is precisely in these places that the T-junction is leaking. I hope that sealing with Dictol will also reliably stop these leaks. The clamping flange components are all printed from solid PETG. For now, I'm going to carry on using tubing for the inertance. The clamps themselves can also be printed, but they are so cheap to buy that it's not really worth it. All components have now been sealed with Dictol, and once they are completely dry, the first test runs will be carried out on a hopefully completely leak-proof engine. In the meantime, I will design and 3D print an adjustable membrane holder with a generator mount and a cover. We will then see whether the charge pressure delivers the expected performance boost. The development of the engine is currently at a very exciting stage, which is sure to bring with it a few surprises and challenges. As always, I would like to hear your feedback, suggestions and thoughts in the comments, on Discord or at ownenergy.org. Your help is absolutely important for further development work. If you would like to support the project further, becoming a member on Patreon or YouTube would be a great help. Every cent from this will be invested in the development of the open source thermoacoustic Stirling engine. Thank you very much for your interest.